Monitors. What are monitors? Monitors that let you see the state of a machine and hence monitor them. If you've ever seen a picture of a really old computer, such as a digital mini computer, PDP something, or a small hobby computer such as the Altair 8800, they will have a bunch of switches and LEDs on a panel somewhere. By modifying switches and pressing buttons, you could store or edit values in the machine, and thus you're able to monitor the machine's state. If you look at a 1084S, you'll see it proudly declare that it is a video monitor. We no longer make the distinction, we just assume the monitor will be video based. The monitor software mimics the switch and LED kind, allowing us to debug and control the computer. I'm going to compare and demonstrate 3 different monitors: the Commodore 128's built-in monitor, the Action Replay cartridge 5-6 monitor, and the WinVICE monitor, which is different to the other vices. There is a small variance in how the commands and features work. The 128 and AR mostly have feature parity in the basic sense. Vice is superlatively more feature-packed. However, each have different advantages and disadvantages. The 128 monitor. I recommend you use the 80 column mode for the monitor, as this leaves the 40 column screen free, allowing you to see the current output and your code at the same time. The escape X key sequence is used to switch. On Vice it is F1 then X in the positional mapping, or F5 then X on symbolic mapping. To enter the monitor, you type monitor into basic, or you can use the basic shortcut MO Shift N. By default it is mapped to F8, although you can use the key command to map it to another F key. You can also hold down run stop, which is escape in Vice, at reset or power on, and it will enter the monitor instead of booting. This is handy if you end up in an infinite loop and have disabled the kernel. Side note, booting this way doesn't destroy a basic program, so if you lock up in basic, you can use this to recover your basic program. When you enter the monitor, it will show you the current status. A 5 hex digit program counter. This is due to it being 128K and needing more than 4 digits. The status register. These are the flags such as negative, carry, etc. Sadly, the 128 monitor does not break these out to individual flags. The accumulator, or A register, X register, Y register, and the current stack pointer. If you wish to review or change any of these values later, you can use the R command and modify the values in place. To enter data into the monitor, you will use the greater than symbol, followed by the address. The 128 monitor is lax and will accept 1 to 5 hex digits for the address, and up to 16 numbers. Numbers can be 1 or 2 digits in length. Any numbers after the 16th are ignored. Let's check that I actually entered the code I think I did. For this, we use the disassembly command, D. D will show a standard length from the current PC, or you can specify the start address and optionally the end address. A handy feature of the 128 is you can stop scrolling, while the 64 let you use Control to slow scrolling. You can now also use scroll lock, F8 positional, F12 symbolic, to halt scrolling. Press again to resume. I've entered the code with a break, so when it runs, it will enter back into the monitor. To run our code, we use the G command to go. If you give no address, it will jump to the current PC. If you want to end routines in RTS, you can use the J command. Well, that didn't do anything. This is a 128 trap. The banks. It doesn't just use the first digit as 0 or 1, it uses all 16 values. 0 means pure RAM bank 0. So my code did exactly what I told it to. It wrote 0 to DO20. Only DO20 RAM, not DO20 VIC chip. FBank means RAM 0 plus all ROM and IO. See page 28 of the 1 to 8's PRG for details. So let's try again, but this time in bank F. And the color changed. However, note the PC when we enter. Break has a 1 byte param that is thrown away, so the PC is +2 from the actual breakpoint. Let's use M to modify some memory. I will change the color and run again. Luckily, the 1 to 8 monitor features the assemble command, so we don't have to enter code in hex, A address or dot address, first line of code. The parser is very lax. You can skip dollars, you can skip leading zeros, and you can use plus before a number to enter it in decimal if you prefer. When looking for addresses in the future, you just enter a dummy value and then go back up and fix them once you know the actual address. While the code fits on one screen, this is fine. Once you get past a single screen, it gets a bit painful, and you'll probably need to do a code, then disassembly review to fix them all up. But at this point, start thinking about using an assembler. This is something the AR monitor excels at, as you'll see when we get to it, as you can freely scroll the code up and down. If you forget a line, the 1 to 8 comes with the ability to insert blank lines. Escape I. You can also delete a line with Escape D. Sometimes you will want to type on a line, but it already has stuff on it that will cause issues. Escape Q will clear from the cursor to the end. So let's run this new code. It should print hello with a space between each letter at the top of the 40-column screen. Well, that was uneventful. Guess we have a bug. So in order to debug code, we insert breakpoints into the code and then check the value of registers, then restore the correct value and G again. Let's make sure I'm reading the value I expect. So I will set 2007 to be a breakpoint. But first, I need to write down what is already at 2007. C9. Breakpoint set. Let's run. Okay. A is 8. That is what I expected. So why doesn't it display on the screen? So I need to remove the breakpoint. So set 2007 back to C9. And I'll put my next breakpoint at 2000 B, which currently has 99 at it. So write it down. Set. And we go back to 2007. The PC is 2015. That is not what I was expecting. So we read 8, we get to 2007, but we don't get to 2000 B. Oh, I'm an idiot. B, Q, not B and A. Just patch the code. And let's go again. We hit 2000 B and A's 8 as I expect. So now I need to remove the breakpoint. What was it again? 99. So set it back and go 2000 B. And there we have hello on the 40-column screen. As you can imagine, this gets old fast. It's slow, cumbersome, and error-prone. At some point you will write down the wrong value, read the wrong value, or forget to subtract 2 from the PC to restart the code. Then the code gets trashed, or the code does random things and ends up in the nullarbor, and you have to hold run, stop, and reset to get control back and try and repair the damage. However, this is fairly simple stuff. It is easy to automate, and the 1 to 8 assists greatly in this task. 80 columns. Such extravagance, really. You don't need 80. While having 16 bytes per line of memory view is nice, you get by just fine with 40. But even then, extra wide memory only needs 70. So we could shave off the last 10 and use it as a scratch pad. But I don't want to have to keep doing it by hand. All it needs to do is take an address, store the value that is at that address, and store a 0 to it. Then later put the original value back. The window command comes into play here. In a single basic command, which also has kernel access, I can shrink the window the editor will modify, allowing me to preserve part of the screen. So I've knocked up a small basic program. It makes 3 windows. I save the top line for a command input. Just load it up and run it to install. So now I can press F1 to exit the monitor and enter into my breakpoint manager. A address will save the value, set it to 0, and display the address and value on the right. I can then use R to remove the breakpoint, and I'll put the original value back. And exit will exit this manager and go back into the monitor. The proper way to do this would be to hook the IVEC, which is the monitor command parser, so I could just add commands to the monitor itself, but for this example, it will do. Although it is broken, to be fair. So a quick demo. Let me just break the code again. Okay, so let's put breakpoints at 2007 and 2000B. Back to the monitor. So, read the first value, got 8 as expected. I don't care about this breakpoint anymore, so I'll just remove the breakpoint. Double check it to be sure. Good to go. And now we're at the end of the function. The OB breakpoint didn't fire. B and E. Yay, we hit the breakpoint. I'll just remove it. And we'll continue. Since A was 0, you can now see an at the start. This is just scratching the surface of what you could do. Once you get into using an assembler, you really need your labels file, so you know where things are in code. The VDC in the 16K config has 6K just sitting there doing nothing. If you don't want the upper and lower case char set in any column mode, then that gets you another 4K for 10K of RAM outside the main 128K. So you could easily add another window split, say make it 6012/8, and then write some code that will load the labels file from disk, store it into VDC RAM. Then make a simple up and down viewer for the data. The VDC has a DMA controller which makes such things a bit simpler. Then you can have your code labels and breakpoints. Even then, 24 breakpoints is over the top. You could split it on the Y to add another small window to some data. Maybe make a variable watch window. Upgrade the VDC to 64K and you now have 58K of spare RAM. You probably could store most, if not all, of the actual source code at that point. Limitations. Firstly, you need to have the 128 OS running, so memory below 1 COO needs to be intact, except the memory locations you are allowed to use. You can, however, ditch BASIC. The monitor does share some resources, namely it uses jumpfar, JSFar, comparefar, and LDAFar to do its work, so if you break between setting up such a call and then calling said functions, it will have the wrong data for the call, which will break your code. Also, you need the default kernel IRQ to be running, or at the very least to have the default keyboard scanning routines called. You have to make sure your code works in the 128 OS. You also cannot debug anything that is time critical. The machine does not stop, the VIC and VDC keep drawing, CIA timers keep counting, disk keeps sending data, tapes still turn, etc. You cannot debug an NMI that fires multiple times. As you'll break, NMI will fire. Break, again, and you will not have time to react and get out of the loop. The AR5 Plus monitor. Like the 128, you enter it by typing monitor. Unlike the 128, the shortcut is MON. Like the 128, it is mapped to F8. Unlike the 128, you can't change it. Upon entry, you are greeted with the current state of the machine, a 4-digit hex address for the program counter, the A register, aka accumulator, the X register, the Y register, the stack pointer, the CPU01 register used for banking, and the AR card breaks the status flags out individually. Let's enter some code. The AR monitor uses colon for data entry, and it is very strict. You will type 4 hex digits for the address. You will type 2 hex digits per byte, and you will type 8 digits on a line. For this reason, it is usually best to view, then modify, but that is getting ahead of ourselves. To view the code, to double check, we use the disassembly command D. Unlike the 128 monitor, it will only show one address if you only say one address. A lovely feature of the AR monitor is its ability to just keep scrolling up and down. F5 will auto-scroll up memory and F7 down memory. Cursor down or run stop will stop the auto move. This is very handy as when it stops it will give you a clear line to use. For the AR cart you can end with either RTS or break and it will return to the monitor. And there is only the go command G. Since I've used break, it will cause it to enter the freeze menu, as I was not already in the freeze monitor. If you issue a break from the freeze monitor, it will automatically enter back into the monitor. To test that the code did what we expect, we can use the T option on the freeze menu. Return is used to exit the text editor. Let's change it. Using the memory view command, M, as per the D command, will show you one line unless you specify a range, and you can scroll to see more. White will do. The R cart also has the assemble command A, or greater than, address, first line. The parser is very strict. You will use dollars. You will make sure all values are 2 or 4 digits as they need, and if you forget, be sure to remove any question marks on the line, or you'll get another question mark. The editor otherwise is 64 standard. No handy insert lines, remove lines, or clear line codes. But now when you go over a screen of code, you can easily go up and down the code. For data entry, you must remove the space after the colon, or else it will just show you the current PC and not modify memory. Okay, let's check this code. We need to go to the C view. Nothing. We have a bug. Debugging is the AR's strong point. It has automatic breakpoint fix-up. It also has break and freeze points, and it supports up to 5. However, they can only be set and used from the freeze monitor, not the basic monitor. Breakpoints are as we saw on the 128, it will set break, and then that will cause it to enter into the monitor. To set a breakpoint, you just enter SB as the first hex digit on a line. So let's put it on 2007. You can see it has changed to a break. Now if I look at 2007, you will see that it has automatically removed it for me. It will remove all 5 active points upon entry to the monitor, not just the one hit. So A is 8, which is what I expect. However, note that the PC is 2007. The AR card monitor removes the 2 for you. Let's put a freeze point on 2000 B. To do this, you put SF as the first hex byte on the line. Note that this has put a JSR DFD3 on the line. You can remove them by putting CB and CF, respectively. And we go again. Since the PC is corrected, you can just G. 2013. That is not what I expected. Let's look at the code. Note the ranges are not inclusive. It stops before the last value, not on it. And that my freeze point has been removed even though it was not hit. B and E. BEQ fixed. And let us go again. Now back to the text screen editor. Hello. Why breakpoints and freeze points? Well, breakpoints only need 1 byte to place. However, you must have the kernel banked in, and you must have 0316 untouched, so the break vector will call the AR card. Freeze points need 3 bytes, but don't need the kernel or 0316, but it does still need I/O to be banked in. This means you can only use breakpoints if you keep the 64 OS running, and you can only use freeze points on cases that allow 3 bytes. For example, this code. You cannot put a freeze point on the LDA 6 line, as it will corrupt the SDA, which is branch 2, which will cause your code to crash. Apart from that, the card is fairly light on limitations. The other limit is again the machine keeps going, so you can't break or freeze on something that is time critical, although the freeze card will halt interrupts and NMIs for you, so you can break or freeze on them. Just you need to be able to handle values being reset when you return, such as timer values, interrupt acknowledge reads, etc. So if something was relying upon a chip not having something acknowledged, so it won't re-trigger post-freeze, it may trigger again. For me, the 1-to-8 solution is nicer for learning. The scrolling code is a very nice feature, however the very strict parser really detracts for me. Having 2 screens, but you have to switch between menus, is a bit of a drag. The auto breakpoints and PC fix-up is amazing. Neither is perfect. It's a matter of what is more important to you, I guess. The WinVICE monitor. To access the WinVICE monitor, you either use the menu under File or Alt+M. If you're using some other version of Vice, it's Alt+H. When you enter the monitor, you are not given the current state of the machine or device, only the current device and program counter. C means computer. If you're looking at drive 8, it would have been 8, 9 for 9, etc. WinVICE offers additional windows: the register window, the memory window, and the disassembly window, which always resorts back to PC. The register window shows you the PC, 4 hex bytes, the A register, X register, Y register, and stack pointer, the CPU 0 register, and the CPU 1 register. Status flags as a byte and broken out to individual flags. The R command, which also shows you the status, adds the current VIC line, and then the cycle on said line, and the current stopwatch value. This is because, unlike the 1 to 8 and AR monitor, the machine is actually frozen, so the VIC is also frozen, and you can see the exact point it is frozen. For most part, the syntax matches the 1 to 8's monitor. Greater than is used to set data. The VICE monitor is lax, not as lax as the 1 to 8, but you can skip leading zeros. The memory set command probably has a limit on the number of numbers you can add at once, some internal buffer, but it's probably large enough for it not to be a concern. Let's check to make sure it's what I think it is. For this, we use the disassembly command, D. As for the 1 to 8 monitor, D will show a standard number of items. If no parameter is given, it will use the current PC, and you can specify a range. Unlike the 1 to 8, you cannot slow or stop the printing. On WinVICE, you cannot scroll the window. Other versions of VICE don't have this issue, however, they don't have the other windows. Also note that the ranges are inclusive, and sometimes with the disassembly, will go over one. Let's run the code. G is again used. Since it ends in break, it has entered into the 1 to 8's monitor, as this is X1 to 8. There is no way to make it automatically go back to the VICE monitor. Well, there is, but I don't recommend it. However, as we'll see later, this isn't an issue. Let's change the color. This is VICE's crippling deficiency. It doesn't have a screen editor, it has a terminal line. So while you can press up and down to get the previous values you have typed, you can't just go up the screen, change one bit of it, and press enter. You have to type it out. And go again. As you have probably guessed, VICE has an assembler built in, and it's on the A command. The assembler is 1 to 8 spec, but now you can also use the percentage to enter values in binary. VICE also has a rad command that lets you change the default radix. However, the parser is a bit lopsided. In the default radix of hex, you can skip a dollars on address, however, you must place it after a hash for an immediate value. The lack of ability to go back up does make entering code painful. Also, if you make a mistake, it takes you out of assembly mode and you have to do another A command. VICE is a debugging monitor, not a writing monitor. So let's run this code. Oh look, nothing happened. Guess we have a bug. This is VICE's tour de force. Nothing. No single piece of hardware can even hope to come close to the power of the VICE debugger. It has breakpoints. However, unlike the 1 to 8 or AR monitor, it doesn't modify a single bit of the C64 or 1 to 8's RAM. They exist outside the emulation. To add one, you can use the break command, or BK for short. You can also click on the line in the disassembly command. Clicking again disables them. So we hit the breakpoint. The code window is now helpful as we are at the PC. And A equals 8 as we would expect. Now I'm not going to set another breakpoint, that would be pointless. But we now have the step command on Z. So we went to 2009, then to 2013. Oh, the B and E, not B and Q. Let's just fix it. And we'll go again. Since I did not disable or remove the breakpoint, we've hit it again. Now let's see what happens when I step. And the code took the value and stored it at 400 as expected. Oh, we hit the breakpoint again. To disable the breakpoint, we use the disable command, DIS for short, and the number which is printed after the hash. If I never want to stop here again, then I can use the delete command, DL for short, and it likewise takes the breakpoint number. If you want to skip a number of instructions, Z takes a parameter. number of instructions you want to skip. If you don't know how many it is, say a loop like we have here, you can use the until command, UN for short. It takes an address and it will run until that address is hit. So we're at the end of the function, but if we look at the window, we can't see any text on the screen. This is because it hasn't been drawn yet. The machine is frozen, and the VIC is now on line 2 or 3, and the first line of text isn't until line 50. We can use M to check. The numbers look right, but since it's screen codes, the ASCII on the side doesn't help much. For this case, we have the inspect command I. Also worth noting, I is available on the AR card. There we go. And if I exit the monitor with X and go back to the 1 to 8, we'll see it on the screen as well. This is just scratching the surface of helpful debugging tricks and features of WICE, and I'll cover those in a future intermediate video. For this video, I just wanted to cover what a book from the day might tell you to do, how it was done, and how to do it in other monitors to save you the pain of using Supermon or Hesmon or some other generic monitor from back then. My advice to using the old books and learning is use X1 to 8. Use the 1 to 8 monitor to enter your code, and use WICE monitor to debug and step through the code. If you insist on doing it on real hardware, buy a 1 to 8, or at the very least, get an AR card or something that mimics one, such as the Easy Flash 3.